Hi and welcome to Module 3 of 2070. So in this module we talk about modern portfolio theory, where the focus here is on the relationship between risk and returns of an investment. So the learning objectives for part 1 of Module 3 include the following. Firstly, we introduce the concepts of risk and return. What do we mean by risk and return in finance, right? We then look at how they are measured. We look at a few exercises where we measure risk and return using a probability-weighted measure. We then introduce the concept of risk aversion and the utility function, which are the building blocks of financial theories. We then look at portfolio assets. We look at asset portfolios, risk and returns. This is the lecture outline. So let's go straight to it. So the focus of this topic is on describing the relationship between risk and return. So the key question here is, how much should an investor charge for providing financial supply to a certain project, right? So recalling from module 1, we say that the time value of money implies that the value of $1 today is not the same as the value of $1 in 1 year's time, right? So $1 today, or the present value, should grow over time, and the growth rate of money from time 0 to time 1 is described by the rate of return, right, or the discount rate. Okay. So the discount rate here is the rate of return that a certain investor expects from investing $1 today, right, in your project. The required rate of return reflects the time value of money. So by investing in your project, the investor foregoes the returns on an alternative investment, and also they have to bear the risk, right, that they have to bear some uncertainty that the firm does not pay back the money in the future. Yeah? So you could therefore think of the required rate of return or a discount rate as comprising two components. The first one being a risk-free component, or this is the opportunity cost, right? So the first component being the opportunity cost of money. So I suppose that you have two options. One, investing in a risk-free bond, so a government bond. The second option is to choose to invest in, say, CBA, for example. So the risk-free government bond represents the opportunity cost of the investment. However, investors recognize that different companies or different investments have different risks, and therefore, on top of the risk-free rate, investors require a risk premium, right, depending on how risky the particular company is or a particular project is. Yeah? As a result, we would expect that if a project has a higher risk, the investors would require a higher rate of return. Yeah? So risk in finance, we think of risk as the uncertainty of the outcome, right, of the investment. So for example, within today until the end of year 1, CPA might go bankrupt and you can't recover your investment. Yeah? So the question here is, how do we measure returns and risk, right? So what is the best way that we can measure risk of a project and then the returns accordingly, right? So how do we set expectations for risk and return? This is when we introduce the concept of the normal distribution. So in statistics, if we have a normal distribution, we can describe the distribution using two things. The first one is the mean, and the second one is standard deviation. Yeah? So we could think, therefore, of an expected return. We could therefore use the mean of the distribution as the estimate for the expected returns. and the standard deviation, or how dispersed the distribution is, as our measure of risk, right? So we mentioned before that risk is, we think of risk as the uncertainty of the outcome of the investment. Yeah. So I suppose that we could observe 10 different probabilities of the actual outcome of the investment. Then risk is measured by the deviation or the dispersion of these 10 different outcomes, right? So with a normal distribution, it looks like a bell shape where the whole distribution could be described by only two things, right? So the mean, which is here, and the standard deviation, which is how dispersed the distribution is. So in statistical jargons, the mean and the standard deviation are the first two moments of a distribution, right? If we don't have a normal distribution, if our distribution looks something like this, then we need more than just these two measures to describe a distribution, right? So our measure of risk and returns therefore have to change a little bit. The normal distribution is the simplest form of statistical distribution that we have, and therefore we normally build statistical models based on the normal distribution. So how do we use the normal distribution in finance, right? So the problem of the investor is how do we estimate expected returns and risks? Yeah, so we look at an investment is in the future, right? So how do we form an expectation for risks and returns? So one way we can do that is we can estimate all the possible outcomes in the future, and we estimate the probabilities of these different outcomes, right? So I suppose that once we estimate all the different outcomes in the future and we work out the probabilities, we plot all the different outcomes on the plot, we find that the expected returns follow this kind of distribution, right? So what we have here is we have a curve that shows different levels of outcome. So the horizontal axis is the returns, right? And the vertical axis shows the probability of the returns. So suppose that we have returns that follow this normal distribution, and we work out that the mean of the distribution is 10%, and the standard deviation of the distribution is 20%, right? So what does it tell us? It tells us that 50% of the time we would expect the return to be 10%. However, the actual return could deviate from this expectation, and the deviation is described by 20%, right? So the standard deviation tells us how dispersed the distribution is. So by looking at this graph, what it shows us is that, so this is one standard deviation here. So within this range here, what the distribution tells us is that we would expect that for 68.26% of the time, the actual return would range from somewhere from minus 10% to 30%, right? If we are looking at two standard deviations away from the mean, then what it tells us is that we would expect 95.44% of the time, our returns would be somewhere from minus 30 to positive 50%, right? So the normal distribution therefore allows us to ask questions like, what is the chance of losing 30% or more, based on our observation, based on our expectation about future outcomes, right? So if we want to look at the chance of losing 30% or more, we are looking at those observations over here, right? So we're looking at the chances of returns falling below this level, yeah? So minus 30 is exactly 2 standard deviations below the mean, yeah? So we know from before that from here to here, this region over here contains 95.44% of the whole distribution. Therefore, the other two tails that we're looking at here contains about 5% of the distribution, right? So 4.5%. Therefore, the chance that the returns is lower than minus 30% is 4.5% divided by 2, so that's about 2.5%, right? 2.25%. Yeah. So using the normal distribution, we therefore can estimate that the chance of returns being lower than minus 30% is about 2.5%. Right. We then look at another example of the normal distribution. So suppose that we have two companies, right? We have company B and company A, and using either historical data or probabilities, we plot the distribution of the returns for these two companies, right? So for company B, we see that it's a little bit higher, whereas for company A, the returns tend to be a little bit more dispersed, right? So, and they both have the same expected level of return, which is 13%. So based on the shape of the distributions for the returns of A and B, which company do we expect to be more risky? Right. So looking at the distribution, we can tell that for company B, this distribution over here, the chance that the returns, the deviation of the actual return from the mean is smaller than the deviation of the return from the mean for company A, right? So this standard deviation here is smaller than the standard deviation of company A's distribution. Therefore, company B's returns tend to be less volatile than company A's return. So by looking at the distribution here, we therefore can conclude that company B is safer than company A. Right. So we mentioned before that the required rate of return for a certain project reflects two things, right? It reflects the risk-free rate or the opportunity cost of investment, and also it reflects the risk premium of a certain investment, right? And higher risks should be compensated by higher returns. So it's interesting to see that if that's the case, if investors always try to maximize returns in their financial investments, why don't we see people taking infinite risk, right? So why don't people take excessive risk so that they can get infinite returns, right? So if people do indeed maximize expected returns, we would see the return and risk relationship to go on forever, right? So investors, therefore, in theory, they should take infinite risk to be able to get infinite return, right? Some investors should be doing that. But in reality, we don't see investors taking on excessive risk, right? In normal business conditions. So one possible answer here is we're talking about expected risk and returns, but how about investors' satisfaction, or how much investors value an additional level of return, right? So the reason why investors don't take infinite risk so that they can get infinite returns is maybe because they put different values for different levels of returns, right? Therefore, we introduce a concept of utility in which we measure the investor's satisfaction out of a certain investment. So what do we mean by utility? Yeah, so what do we mean by the utility of an investment? So utility is a concept where we try to measure the satisfaction or how much value the investor assigns to a certain investment, right? So the theory here relies on the assumption that investors try to maximize expected utility and not expected wealth, right? So we mentioned before when we look at a normal distribution that investors' returns and risks have a positive relationship, and therefore if investors try to maximize returns, we would see that some investors take infinite risk so that they can enjoy infinite returns, right? Here the theory says, the expected utility theory says that actually investors are not trying to maximize their wealth, they're trying to maximize the utility of their wealth, right? Consumption opportunity, returns and utility are positively correlated. So here the theory states that the investors are not expected to take infinite risk because the expected utility increases with wealth but at a diminishing rate, right? So what do we mean by that? So what do we mean by a diminishing marginal utility function, right? So for the moment, just forget about the numbers on the graph for the moment. We're just looking at the shape of the curve, right? This is a concave curve, and what it means is that if you move from say A to B, so if you increase your wealth by $1,000, your utility increases from U1 to U2, right? If you move from B to C, so you move by the same amount of wealth, right, $1,000, your utility would increase from U2 to U3, okay? But as you can see here, the distance from U1 to U2 is larger than the distance from U2 to U3, meaning that at the higher level of wealth, the utility increases, but at a smaller rate, right? Okay, so the expected utility function or the expected utility theory states that the investors assign a diminishing marginal utility function to investments, right? So in the face of uncertainty, investors' utility increases with risk, but at a lower rate, right? Therefore, at a certain point in time, the increase in utility is too small. That is not worth the risk for the investors, right? So, for example, if we have two options, right? If the investors are given two options, option A is to get a sure gain of W star. Option B is to have a situation where there is a 50% chance of getting U star plus $1,000, but at the same time there is a 50% chance of losing $1,000, right? So the expected wealth from these two different outcomes are the same, which is W star. But for an investor with a diminishing marginal utility function, the utility from option B would be different from the utility from option A, right? So for option B, given the expected change of wealth, the expected utility from this investment is only this much, right? So at W star, the expected utility from the investment is the average of U1 and U3, right? So somewhere in between here. However, because the investor has a diminishing marginal utility function, their required utility, their expected utility is at this level over here, which is U2. So if you compare the expected utility level with the expected utility from the investment, from option B, you will see that option B's utility is lower than the expected utility for the investor, right? And therefore, for this investor, they will not like option B, right? So option B is not optimal for them because it's below their expected utility, right? So the marginal utility function is a function that describes the behavior of a risk-averse investor, right? So for this investor, if you want to ask them to take some risk, right? So if you want them to pick option B, you have to give them a little bit more than before, more than W star, right? If you want them to take option B with a bit of uncertainty, you have to compensate them at U2, right? So if you plot them on the graph, the expected wealth from the investment should be somewhere here, right? So the implication here is, in the face of uncertainty, a risk-averse investor or an investor with a diminishing marginal utility function, they would require higher return, right, to compensate for the risk. So the marginal utility function, therefore, is the foundation of finance theories, right, where we try to model the behavior of a risk-averse investor. So the utility function is therefore a function of expected returns and risk. And given the risk aversion of the investor, we have an efficiency theorem where, given the choice of investments with equal expected returns, the investor would pick the investment with the lower risk, right? And vice versa, if the investor has two different options with the same level of risk, they will choose the one with the higher level of returns, right? So investors are risk averse in the sense that they require higher return for risk. So we mentioned before that for a risk averse investor, they want to maximize their utility. And to maximize their utility, they want to pick the level of returns they want to pick a higher level of return given the same level of risk, or they want to pick a lower level of risk given the same level of returns, right? If they're given different choices. So what we have here is we have utility indifference curve, where any points, any combinations of assets, any combinations of risk and return along this line give the investor the same utility, right? So any point here is efficient point in the sense that at this level of risk, this is the maximum level of return that the investor gets, right? At the current state of the economy. So the investor, if they choose to pick this level of risk, they get this level of return. If they choose to bear a bit more risk, this is their expected level of return. But these points are the same in the sense that they have the same utility for the investor. Right. We have an increase in utility if we have an upward shift of the utility curve, right? So if we move from curve B to curve A, that's when our level of utility increases. But any point along one utility curve gives us the same level of utility. So in the next few slides, we'll look at measuring risks and returns for individual assets. So we mentioned before that we measure returns and risk using the normal distribution. Yeah. So with the normal distribution, the distribution shows us the probabilities of different outcomes in the future. Yeah. So the way that we measure returns is therefore just a probability weighted average of different future outcomes. Yeah. We could use past returns to measure, to estimate future returns, but past returns are in the past, right? So we're looking backward. So the data therefore might not be as accurate as we use probabilities. Okay. So the idea here is we want to measure the expected return of a certain investment. Suppose that we can estimate n different scenarios in the future, and therefore we get n different estimates of returns. We could also estimate the probabilities of these different outcomes. Our expectation for the returns, the actual return that we get, is simply just the probability weighted outcome. Right. So we take outcome 1 times the probability of the first outcome plus outcome 2 times probability 2, so on and so forth. Right. So the expected level of returns is simply just the weighted average of all the possible different outcomes. We measure risk as the dispersion or the deviation from the mean, right? So we measure dispersion as the distance of the actual outcome from the average outcome. Okay. So what we have here is, once again, we have the probabilities of different outcomes. These measures over here measure the distance between a certain outcome and the mean, right? The expected value. So we square the difference here to get rid of the side of the difference, right? So if we have negative difference and positive difference, when we square them up, we take away the side, right? So the variation of the returns or the risk of the return is measured by the weighted average distance of different outcomes from the mean, right? So this measure over here, the probability weighted square variations, is what we call a variance, right? So we talk about standard deviation before. The variance is simply just the square of the standard deviation. Yeah? So the variance of a return is given by this formula over here. This is simply just the weighted average square difference of the returns, right, of the different outcomes. Right. Standard deviation, as we mentioned before, is just the square root of the variance. Right. The unit of variation or variance is percentage square, and the unit of the standard deviation is just the percentage. Right. Okay, so how do returns actually behave in the real world, right? Do we see normal distributions in the real world? And how are returns related to risk? Yeah. Okay. So what we have here is we have 10 years of quarterly percentage returns for different asset classes in Australia. So we have data from the 1994 to 2003. Right. So what do we see here? Cash or short-term assets, right? Short-term discount securities is the green line over here. The blue line is the 0 to 3 years government bond. The yellow line is corporate bonds, and the orange line, the red line, sorry, is the equity returns, right? So looking at these different asset classes, what do we think about the riskiness of the assets? Cash are short-term securities, right? So they're quite safe. Government bonds, they're quite safe as well, except for that they are a bit longer, so they have a bit more liquidity risk. Yeah. Corporate bonds are a bit more riskier than government bonds. So besides liquidity risk, they also have the default risk of the corporations. Yeah. Equity tends to be more volatile than bonds. So we expect that the risk of equity investment is a bit higher than the other asset classes. So what this graph shows is it shows the time series variations in the returns of these different asset classes. And as we expect, the returns of cash securities or short-term securities is not that much. It's more or less like a flat line, right? Government bonds are a bit more volatile, but it's not very much compared to corporate bonds, or especially corporate equity, right? So equity, being the riskier assets, they also have a higher volatility, right, in their returns. So if we compare the expected return or the average returns of these different asset classes, what do we see? We see that the more volatile asset classes tend to also have a higher expected returns, right? So equity have a higher average return, but they also have the highest standard deviation. Yeah. The returns of these different asset classes are very much similar, and their risks are also quite similar, right? It's striking that the returns, the expected returns for equity, is not too high compared to the other three asset classes, but if you look at the standard deviation, it's much higher. Right? So the question here is it worth it? Bearing the risk of equity, right? Also bear in mind that this is just a 10-year period, so the data here might not be representative of the newer periods, right? The more recent periods. We then look at portfolio risks and returns. So in the previous slides, we measure risks and returns. We introduced the concept of risks and returns for individual assets. Yeah. So return is simply just the average, right? The expected return is just simply the average of all different possible outcomes in the future. Whereas individual assets risk is simply just the variation of different outcomes from the mean, right? So with portfolio risks and returns, portfolio returns are measured in a similar way compared to individual asset returns, but portfolio risk is a bit different. Yeah? So a portfolio is simply just a combination of different assets, right? So we can think of the portfolio as an asset itself, right? As a big asset. Right? So the example that we have here is, suppose that we have a portfolio with equally weighted assets, right? So we have two assets and each of them has 50% of the weight, right? So if we start with, say, $1,000 to invest, we would invest $500 in A and $500 in B, right? So that's what equally weighting means. From the individual assets, we could compute the expected returns for individual assets, and it's given at 15.5% for asset A and 25% for asset B. Right? We're also given the variance of the returns of A and B. So asset B obviously has a much higher variance compared to asset A. Right? So how do we measure portfolio returns? Yeah. So a portfolio return is measured as the weighted average of individual asset returns, and the weight here is given by the proportion that we invest in a certain asset, right? So in the previous example, where we have two assets, A and B, and they are equally weighted, it means that the weight for A and the weight for B is equal, right? Are equal, and they are both 50%. Right? With portfolio risk, it's a bit more complicated than portfolio returns, in that besides the individual asset riskiness, we also have the correlation, right, between different assets, yeah? Because we're combining different assets together, we've got to take into account the fact that these assets might be correlated, yeah? So the portfolio risk is therefore described by three different factors. The first one is the weights of the assets. The second is the riskiness of the individual assets. And the third component is the relationship between the assets. Right. So we talked about variance before, we talked about individual asset risk before. Now we talk about relationship, right? How do we measure the relationship between different assets in the portfolio? So our first measure for relationship is the covariance measure, where it tells us how one asset moves together with another asset. Yeah. So the covariance is given by this formula over here. Right. So if we measure the covariance between asset A and asset B, it's given by the correlation between the two assets times asset A's standard deviation times asset B standard deviation. Yeah. Correlation. So we mentioned before that correlation is simply just how much two assets move together. Yeah. So from the formula before, we can work out that the correlation of two assets is simply just the covariance divided by the product of the standard deviation of asset 1 times asset 2. Right. So as you can see from their formulas, the covariance and the correlation are basically very similar. The only difference here is that for the correlation measure, it's a standardized measure in the sense that it ranges from -1 to 1, right? So it tells you, it's more or less like a percentage number, where it tells you how much asset A would move when asset B moves, right? So if the correlation is 50%, it means that if asset A moves by 1 unit, asset B would move by 0.5 unit, right? Okay. So if we have assets with negative correlation, this is how the asset returns would look like, right? So for these two assets, asset 1 and asset 2, we have a negative correlation with a very large magnitude, right? So they tend to move nearly perfectly opposite each other, right? So when asset A moves up, when asset 1 moves up, asset 2 moves down, right? So when one increases, the other one decreases. When we have positive correlation, when asset 1's returns increase, asset 2's returns also increase, right? So they tend to move together. So which assets are highly correlated and which assets are not very correlated, right? So in reality, if we have assets that are in the same industry, if we have companies that are in the same industry, they tend to move together. For example, when we have PHP and Woodside, right? So they are energy companies, they're in the same industry. Their cash flows are therefore very closely correlated. Yeah? Whereas if we compare an airline industry and an energy industry, their correlation is not that high, right? So for an asset, for a two-asset portfolio, this is how we measure the variance of the asset returns, right? So the variance of the asset return is given by the weighted variance of the first asset plus the weighted variance of the second asset plus the covariance, the weighted covariance of the two assets, right? So this is where the correlation of assets influence the variance of the portfolio, right? If you have a smaller correlation, then what happens is you would also have a lower variance of the portfolio, right? Alternatively, if you have a high level of correlation, then your variance would also be a bit higher, right? So this formula provides the foundation for diversification, right, which we'll be covering in the next in part 2 of module 3. So for two assets, if we have a portfolio with two assets, we could describe the variance, the portfolio variance formula using this matrix over here, right? So what we have here is we have the weighted standard deviation of individual assets. So for two asset portfolio, we have 4 different components, right, of the formula, and the variance of the portfolio return is just the sum of these 4 different components, right? In the case of a 3-asset portfolio, we basically do the same thing. We have the weighted standard deviation for 3 different assets. We times them together, and so we have 9 different components, right? The variance of this portfolio is therefore given by the sum of these 9 different components, yeah? This one here is the same as this one over here, right? This one here and this one here are the same, and this one come to here, right? So for a 3-asset portfolio, the variance of the asset portfolio would be comprised of 3 weighted standard deviation squared plus these 3 different terms over here, right? So to generalize the formula, if we have an n portfolio assets, if we have a 2 portfolio assets, we have 4 different terms, right? If we have an n portfolio assets, we therefore would have n square terms, yeah? So we have n variance terms, and we have n square minus n pairs, right? Different pairs. So For an asset portfolio, we have n squared terms, n variance terms, and n squared minus n divided by 2 pairs. Yeah. So going back to our example on slide 21. So what did we have before? We had two assets, right? We have asset A and asset B, equally weighted. Yeah. Asset A's return was 15.5. Asset B's return was 25%. Right. So because they are equally weighted, they both carry 50% of the weight. Therefore, the expected return for this portfolio is simply just the average, right, of 15.5 and 25%. So that's 20.25%. So to calculate the portfolio risk, we use the variance formula that we saw before, right? So we have a 2-asset portfolio, and according to the calculation, not the calculation, but according to the previous slide, we know that for a 2-asset portfolio, for the variance, we have 4 terms. We have 2 variance terms, and then we have a pair of the correlation term, right, or the covariance term. So using this formula, we then work out the variance of the portfolio, and from the variance, if we want to work out the standard deviation, we take the square root, right? So remember the unit of the variance, it's percentage squared, right? Because we're squaring the standard deviation of individual assets, yeah, right? Okay. So that concludes part 1 of module 3. So in this part, what we went through the basic calculations of individual risk and return based on the concept of a normal distribution, right? We then introduced the risk-averse investor. So we mentioned before that investors don't take infinite risks because they try to maximize the utility, and the utility function is a diminishing marginal utility function. Right. So given that the investors are risk averse, they don't take infinite risk because the more risk that they take, the less satisfied, right? So the less utility that they get out of the investment. Right. So in the face of uncertainty, the higher risk or the higher the uncertainty of the investment, the higher required utility. Right.